Electron configuration. The number of numbers in the configuration tells us how many occupied principal energy levels there are. In the case of carbon, the atomic number is 6. Subsequently, the number of electrons is 6 in its elemental form. Thus, the electron configuration is 2,4 because the sum of 2 and 4 is 6. And in this case, based on what we've just discussed, there are 2 electrons in the first principal energy level of carbon, with 4 electrons in the second principal energy level of carbon. Now, if we answer these questions based on magnesium's electron configuration, the electron configuration of Mg is shown here as 282. There are 3 principal energy levels in Mg, and there are 2 electrons in the first PEL, 8 electrons in the second PEL, and 2 electrons in the third PEL. Each principal energy level has a specific magnitude of energy associated with it. The principal energy levels that are farther from the nucleus have more energy than the principal energy levels that are closer to the nucleus. The principal energy levels that have a greater number associated with it. So for example, the fourth PEL has a greater amount of energy than the second PEL because it is farther from the nucleus. Each principal energy level has a capacity for a certain quantity of electrons. You don't have to necessarily remember all of these, but I would suggest to remember the first 3 or so for a high school chemistry course. The first PEL has 2 electrons, the second has 8, and the third has 18. We will get to why these quantities are what they are when we discuss expanded electron configurations later. As we've established, a further principal energy level from the nucleus of an atom will have a greater amount of energy associated with it. The outermost occupied principal energy level in an atom will be referred to as the valence shell, and electrons in that shell are denoted as valence electrons. These are also referred to as bonding electrons, which we will discuss in a different video. In this example, Mg has 2 valence electrons because there are 2 electrons in its third and outermost principal energy level. When all electrons in an atom are in the lowest possible energy level, this is the ground state. The electron configurations on the periodic table are the ground state configurations of an atom. However, this isn't always necessarily true, as atoms can absorb energy, and thus the electrons in the atom's shells will move to a greater principal energy level, and the atom will be denoted as being in the excited state. The periodic table and the maximum number of electrons in each energy level can be used to determine if an electron configuration is represented in the ground or excited state. Determine if the following configurations are in the ground or excited state. So in this configuration, we have 284. Now, this would be the electron configuration of silicon. And as we know, the capacity of electrons in the first PEL is 2, and for the second PEL is 8. So thus there are 2, since in this depiction there are 2 and 8 in both of those PELs, we can assume this is in the ground state. In this case, since there are only 7 electrons in the second PEL, whereas it could hold 8. This is an example of an electron configuration that is indicative of the excited state. The same applies to the third electron configuration, since the first PEL has a capacity for 2, where in this case only 1 electron is there. This is also indicative of this atom being in the excited state. The periodic table and the maximum number of electrons in each energy level can be used to write a possible excited state configuration for a given element. Electron configuration practice. Question 1. An orbital is a region in an atom where there is a high probability of finding an electron. The answer for question 1 is B. Question 2. The electron configuration of an atom in the ground state is 2, 4. The number of occupied PELs in this atom is B2. There are 2 PELs in this depiction. Question 3. How many electrons are in the outermost PEL of an atom of carbon in the ground state? Now, if we look at our periodic table, the electron configuration of carbon are as follows. There are 2 electrons in the first PEL and 4 electrons in the second and outermost PEL. Based on this analysis, there are 4 electrons in the outermost PEL. Thus, the answer for question 3 is D4. Question 4. When an excited atom in an atom, when an excited electron in an atom, my mistake, moves to the ground state, the electron, now we haven't discussed this yet. However, when an atom moves from the excited to ground state, it is moving from a state of higher energy to a state of lower energy. Since it is losing a quantity of energy, it has to emit that energy. Now it emits that energy in the form of photon emission or as light. So for question 4, the electron emits energy because the electron is moving to a lower energy state. The answer for question 4 is D. Question 5. An electron in a sodium atom gains enough energy to move from the second to the third shell. So since it's moving from a region of lower to higher energy, it is becoming an atom of the excited state. The answer for question 5 is C. Which electron configuration represents the electrons of an atom in an excited state? The answer is B, because in B, 7 is less than the maximum capacity of 8 for the second PEL. Thus, the answer for question 6 is B. A bromine atom in an excited state could have an electron configuration of, well, if we recall, the third principal energy level has a capacity for 18 electrons. Thus, the answer must be either C or D, since both C and D have a third PEL with a number of electrons that is less than 18. Now, bromine, if we recall, in the elemental form of an atom, the number of electrons must equal the number of protons, and the atomic number is indicative of the number of protons. Since the atomic number of bromine, based on the periodic table, is 35, it has 35 protons. Subsequently, we can conclude there are 35 electrons in bromine in its elemental form. Thus, the sum of the electrons in the electron configuration of the atom must be 35. The sum of 2, 8, 17, and 7 is only 34. Thus, the answer cannot be C. Whereas in D, the sum of 2, 8, 17, and 8 is 35. This corresponds to the atomic number and thus the number of protons in bromine. Thus the answer for question 7 is D. The excited state is unstable because it is electrostatically unfavorable. Electrons release energy when an atom returns to the ground state. When atoms returned to the ground state, they release energy in the form of light, called bright line spectra, via photon emission. Bright line spectra is often referred to as the fingerprint of an element. As we know, fingerprint in mammals is a distinct property that is unique to every individual. This same idea applies to bright line spectra, since the bright line spectra is unique to each and every atom. Here's an illustration that depicts the process of the transition from the ground and excited states. So an atom in a ground state will absorb energy via photon absorption to move to the excited state, in which the electron will move from a lower energy state to a higher energy state that is of greater distance from the atom's nuclei. Whereas if we're transitioning from an excited to ground state, and the electron will move closer to the atom's nucleus and subsequently emit energy via photon emission. As we've discussed, bright line spectra is distinct to each and every element. These are a few examples of this. For example, hydrogen will always have this bright line spectra, whereas mercury will always have this bright line spectra. If we have a substance, we can analyze the bright line spectra to determine the contents of that substance. We can also apply the same idea when analyzing the contents of an unknown mixture, a mixture being a combination of two or more elements. Now in this case, we can easily deduct that this mixture consists of elements A, D, and Z, because the bright line spectra of the mixture corresponds to the bright line spectra of all A, D, and Z. This mixture does not consist of X, because as we can see to the right here, the bright line of spectra of X does not correspond to that of the mixture. Here are some assessment questions on this topic. Each line in the spectra represents the energy. Well, energy is emitted via photon emission, so thus energy is being released. So that leaves us with choices C and D. And energy is released when an electron moves from a higher energy state to a lower energy state. So the answer for question 8 is D. Question 9. Which elements are present in this mixture? The answer is C, because we can easily see that the the bright line spectra, I should say, of the mixture corresponds to that of both A and X. Thus the answer is C for question 9. Question 10. Which electron transition in an excited atom results in a release of energy? So in order for energy to be released, the transition must be from a higher energy state to a lower energy state. So the only answer choice that is consistent with this description is choice D, because it's going from the fourth to the second shell. Whereas in the other choices, it's going from a lower shell to a higher shell. Thus the answer for question 10 is D. The applications of what we've just discussed is mainstreamed in firework colors. Now, in fireworks, there are various organic reactions that occur that will be discussed later in Unit 10 and 15 when we discuss chemical reactions and organic chemistry, respectively. However, the colors that are produced, as we know, when an electron moves from a higher energy state to a lower energy state, it emits photons. Each photon has a different wavelength and frequency associated with it. The wavelength and frequency associated with it is indicative of what color it is. For example, purple, blue, and green colors will have lower wavelengths and higher frequencies than red, orange, and yellow colors, which will have higher wavelengths and lower frequencies. Thus, we can use this principle to predict the colors that will be present in fireworks based on this subatomic analysis of it. Photons are particles of light that comprise waves of electromagnetic radiation. Much of the content discussed here will overlap with that of a high school physics course as well. This is the electromagnetic spectrum, as we've discussed. Green, orange, and red color are indicative of lower frequency and higher wavelength, and green, blue, and more purpley colors are indicative of shorter wavelengths and higher frequencies. Energy increases as wavelength decreases and frequency increases as well. Some background on this is the velocity of a wave equals the product of wavelength and frequency. Since the velocity of a wave, at least in a vacuum, is always 3 times 10 to the 8th meters per second, that is a constant. Thus, if one of the variables increases, the other variable must decrease. So if velocity equals the product of wavelength and frequency, and if that product is constant, if the wavelength increases, the frequency must subsequently decrease, and if the frequency increases, the wavelength must subsequently decrease. Thus, this is why we observe this inverse relationship between a wavelength and frequency. When a photon is absorbed or released by an atom, the energy of such is increased or decreased by an amount equal to that of the photon. The energy of a photon, as we have discussed, is directly proportionate to frequency, and they can be quantitatively connected to one another by using Planck's constant, which is represented by h. So E, the energy of a photon, is equal to the product of its frequency and of Planck's constant h. Frequency is measured in hertz, which is equal to 1 divided by a second, or s to the negative first. As we've already established, frequency is inversely related to wavelength through the speed of light, c. Wavelength is measured in meters. So as we see here, c, the speed of light, equals the product of wavelength and frequency, and energy equals the product of Planck's constant, whose units are joules per hertz, multiplied by frequency. Planck's constant, h, is equal to 6.6 times 10 to the negative 34th joules per hertz. Expanded electron configuration. We've already explored basic electron configuration. However, there is a more rigorous and more truthful, if we want to say, way to express the electron configuration of an atom. This can be done using the energy sublevel of the electron domain of an atom. This can be expressed using the 4 letters S, P, D, and F, which are in reference to the sublevels of an atom. The S sublevel has a capacity for 2 electrons. The P sublevel has a capacity for 6 electrons, the D for 10 electrons, and the F for 14 electrons. The first principal energy level has just a s sublevel. Thus, only 2 electrons can be held in the first PEL, as we have already seen. The second PEL has a 1s and 1p sublevel. Thus, the electron capacity of the second PEL is 8, which is the sum of 2 and 6. The third PEL has an S, P, and D sublevel, and thus has a capacity for 18 electrons, as we've already saw, which is the sum of 2, 6, and 10. And with the fourth BEL, it has S, P, D, and F sublevels, and thus has a electron capacity of 32 electrons, or the sum of 2, 6, 10, and 14. We've already discussed the distinction between basic and expanded electron configurations. When writing expanded electron configurations, energy levels and sublevels will be written in order of increasing energy. The following notation will be used for each energy level and sublevel combination. As we see here, the type of orbital, which is either S, P, D, or F, is represented at central. The energy level is represented to the left of the type of orbital, and the number of electrons in the orbital is represented to the right and above it. Something to note is that the number of electrons in the orbital for an s orbital is always less than or equal to 2. For p orbitals is less than or equal to 6, for d orbitals is less than or equal to 10, and for f orbitals is less than or equal to 14, because these are the respective maximum number of electrons that correspond to each of those orbitals. So if for a moment we can, first, for the purpose of our discussion, let's just assume that this helium here is moved such that it is adjacent to the hydrogen here. Now if we notice, this S block represented by blue is 2 elements wide. The capacity for the S sublevel is also 2. If we look at the P block represented by green, it is 6 elements wide, which is also the electron capacity for the P sublevel. The same idea applies to D and F, since the D block is 10 elements wide, and the F block is 14 elements wide, and both of those numbers, in terms of elements wide, correspond to the capacity of electrons for both sublevels. So if we were to express the expanded electron configuration for, say, aluminum, which is atomic number 13, which would be right here, the second element in the 3A group, right here, where my mouse is, we would do this by writing out 1s2, 2s2, 2p6, 3s2, and 3p2. I hope this discussion made this topic more clear. Example 2. If we did the same for strontium, which is atomic number 38, which would be right here where my mouse is, the second element in the 5s block. Now the expanded configuration for SR would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, and 5s2. You can practice the same idea with nickel. Aufbau diagrams. Aufbau diagrams show the energy distribution between the different sublevels in an atom. The lowest energy orbitals are occupied first, and the sublevels that are occupied subsequently are based on increasing energy levels. when drawing these, include all 7 principal energy levels, even if an atom does not necessarily have electrons occupying them. When drawing Aufbau diagrams, it is important to remember based on the Pauli exclusion principle, to have the arrows facing different directions. Based on the Pauli exclusion principle, the quantum state of 2 atoms in the same orbital must be different or distinct of one another. Thus, the spin of those electrons must be different from one another. This can be represented by arrows facing different directions. So the up arrow would refer to clockwise rotation, and the down arrow would refer to counterclockwise rotation. We cannot illustrate Aufbau diagrams with arrows facing the same direction. This is an incorrect representation of using Aufbau diagrams. Another thing to note is Hund's rule, which states that electrons in orbitals within the same sublevel will occupy empty orbitals before they pair. An analogy I like to use is going on a train in which the various seats have people in it. Now, generally, you would want to sit in a seat that does not have any other persons within it. You would only want to sit next to someone else if there were no other empty seats. This idea also applies to Aufbau diagrams. Now here, this is an incorrect illustration because this electron that is pairing with this electron could have went to this free domain. This is why the above illustration is a correct depiction of the Aufbau diagram, because the electrons are not pairing with one another because they do not have to in this circumstance. I would also like to note that the S or sublevel has one Aufbau domain because its capacity is 2 electrons, or the P sublevel has 3 domains because it has a capacity for 6 electrons, and 3 times 2 would be 6. Now you can practice illustrating Aufbau diagrams for the following elements, but this will be it for this video. I hope you found this video informative. I will be forming a playlist for both PreAP / New York State Regents / any introductory high school chemistry course, along with a playlist for AP chemistry, along with playlists for subsequent chemistry and physics and mathematics courses on the college level. Please feel free to like and subscribe, and I hope I will see you in later videos.